Hi everyone, so today I'll be talking about tilepy, which is a tool that we developed for the observations of poorly localized multi-messenger events, and that has been evolving through the years. So maybe you know already tilepy, but we keep evolving it. So maybe there's some new stuff here for you as well. Okay, so this is the team of people working on the code. This goes back to 2015 when, with the discovery of gravitational waves, when we faced the challenge, okay, that's very pixelated, but when we faced the challenge of what do we do with these rings in the sky that usually we call banana shapes that are provided by the gravitational wave interferometers, when we have two of them that are much better if we have three interferometers detecting, then we have like a nice Gaussian, but many of the times we have this type of localizations, which are very broad. This is not the only time where we find large uncertainties on the localization of sources, although it was really a motivation because we couldn't bypass it. But there's other sources that also show very poorly localized localizations. For example, the GRBs from Fermi GBM that we maybe were waiting for the Swift update on the same event, but that we can also go and tackle them. It's the same case with ice cube cascades. You have there some simulated events, but it's also going to be a future problem because even with Einstein telescope, we are still going to have a large fraction of events that are not really well localized. Remember that this is like a logarithmic scale, so it's a big bunch of them. So, okay, to cover all this, we need observation strategy, specifically if you are a small or mid-sized telescope. This is the challenge that motivated us to develop tilepy. So this is the timeline of the code. We started it back in the day with observing run 02, as many other people in the community had to develop their own tools. So we did that for HESS, gamma ray telescope. So by then it was a bunch of codes, but that were totally making the job. We included it in the HESS VO alerter, so no human in the loop for the reaction. Good thing we did because we could follow gravitational wave 17 and 0817 when we had to. After that, we waited until the end of 02 and 03 to ask ourselves, oh, can we generalize this to other cases? Then is when Fermi GBM entered in the game, and so in our game. So we could also apply tilepy for GRBs. And also we moved to another telescope that was not HESS, but was CTAO LST1. So this is the first telescope of CTAO in La Palma. And then we realized that, oh, the code was getting too big. So we had to modularize the code and make it much modular and nicer. And we were doing this by waves, right? So back then was the first wave, second wave very recently, because also the code was growing too fast. In the meantime, we created the Python package. So it was much more easy to install in our machines and in any VO alerter or transient handler. And then we also expanded to any poorly localized event that has a helpix sky map, but also we can create Gaussians from coordinates, so it becomes a helpix sky map for us, and also to any ground-based facility. So now you can find it in PyP. Actually, don't try to download it just now because there are some little issues, but in general, you can find it. So you can just do pip install tilepy and you have it there. Okay, so this is the story. Okay, last point, we also have it for space-based scheduling, and we inverse the logic, and I'll tell you more about this afterwards. Oh. Okay, so in a nutshell, so this is modular flexible, and it's for multi-observatory, multi-telescope, multi-wavelength. So we try to cover everything. There's the capabilities side, but also the functionalities that can be used standalone or just as an orchestrator that it does its thing, but you don't need to look at the code directly. What's in the code? So basically we have some inputs, which are basically characteristics of the events and what's your configuration of the follow-up. Goes all in a config file, quite big now. And then you have a set of decisions that are made inside the code, which mostly regard the visibility considerations of your telescope, but also how you want to define your windows, which can have a fixed exposure, or it can be an array of exposures, or you can also, this is there for CTAO, you can also say, oh, I want to ensure a detection for how long should I observe. This is for the visibility part, but then we have the sky coordinate part, that we try to improve and cover all the cases. So we covered the case of, let's mask the region we just observed so that we have extended coverage. So you can go from basically this to this. There's also an energy threshold optimization, but it talks to the air mass in optical. So basically, which is the wave or like the conditions of your observation, so that you either observe in like one zenith or another zenith. So in the case of gamma ray astronomy, you want to go to the zenith observation so that you have a decreased energy threshold. But then you can apply this to optical for air mass, etc. We also have an interplay between high and low resolution maps, and then we sort the covered regions as well. Okay, so in terms of the code architectures, there's 4 layers. An orchestrator, observing, scheduling, tiling, pointing tools. Again, this can be used standalone, but many users just want their observation scheduler to be orchestrated and don't look at the different little functions, but you can use them alone as well. And this is how you schedule for the night. Okay, now I'm gonna focus for a moment on the more technical part on the probability selection, because it's a big part of the code, which basically can be done in 2 ways. Either if you have information about the distance, which you do in gravitational waves, then you are gonna do a 3D approach. But if you don't, if you just have Radek probability distribution, then you can use this approach, which is, well, you have a grid of points in the sky and you need to decide which one is the one that you're following, right? So if you have a low resolution map, we can take here, you would start here, then here, etc. This if you don't take into account the visibility of your telescope that is evolving during the night. So what we do here is we take this low resolution map and a high resolution map, and then we can also correct for the effect of the edges, because maybe your field of view is not squared and is not matching this specific squared from the Helpix map. So we have this interplay so that we have less, is less computationally expensive, the computation. So you will have this sort of this grid, and then, okay, which is where's the observation that covers most probability, and it's that one, and it's selected, and the process starts again. Okay, then you have 3D algorithms as well that were that are used in gravitational wave follow-up, specifically because you have information about the distance, and then you can combine this with galaxy catalogs. So depending if your observatory has a small field of view or a mid field of view, you would like to focus on specific galaxies. So this is the galaxy targeted search. Or if your observatory has a mid field of view, or as in gamma rays, then you want to galaxy cluster your search so that you look for clusters of galaxies in your catalog. So for example, in this case, if you're doing galaxy clustering search, you're probably gonna observe here. Instead, if you're using a galaxy target, you will probably start like here and then go tick, tick, tick. This is the case of 170817, how we use tilepy and cover this part, and it's where the host galaxy was located. Okay, you can obviously add more complexity to this game. So one complexity that you can add is physically motivated wavelength for this probability. Like as the one presented here that concerns B luminosity. There's other, some people use K luminosity, some people you're just focusing on stellar mass. So this is one complexity one can add in tilepy, and it's there for the B luminosity. Also second round, because as the night is evolving, there's other regions in the sky that maybe you covered, but now you can cover with better observing conditions. So this is another functionality that is there. You can also update the observing plan based on previous observations. So this is important when you have updates, as you do, for example, in gravitational waves, but also in GRBs. And then there's also one point on overall ranking functions, because due to the visibility evolution, for example, if we take this case, is it pointed? Yeah. So if you take this case, due to the visibility evolution, you would start with 0, 1, 2, 3, and 4 due to the orientation, but maybe the real priority is 2, 3, 1, 0, 4, because this is how it goes when you compute the probability that you cover. There's many cases like this that changes depending on when you start your observations. Okay, so once we figured out how to do it with one observatory, we decided to go multi-telescope. So the idea here is that you need to assess what's the visibility for each of your telescopes. And you do this by having a specific config for each of them that can be very different. And then you will go sequentially and check if you can observe or not, and then allocate observations. So this is there, and here I show you 2 examples. So this is the GRB, a Fermi GBM GRB, where we selected 4 LSTs as an example. So you could see how you could cover the uncertainty region. This is 82% coverage with basically 1 hour and 45 minutes. Depends on the pointing duration, obviously, but you indeed go 4 times faster than if you were pointing all the telescopes at the same time. And then we have here another example for the gravitational wave. One example where, in this case, we are using an integrated 3D strategy, and all the little points you see there are galaxies. Okay, so once we had the multi-telescope case covered, we have integrated the satellite scheduling. This was presented this year in ICRC. So the characteristics that change with respect to the other scheduling is that now the reference frame is the satellite, and that you have other visibility constraints as the South Atlantic anomaly that we are considering as a mask. And also the slewing time minimization is key in this case, and it wasn't such a key point on the other cases that we covered. So this new case made us change or propose a new workflow that, instead of being time window then probability scheme, is rather probability then time window scheme. So this came actually from some discussion last year in this workshop. We have incorporated this possibility in tilepy because it opens an entire new optimization, let's say, field, because you're gonna have basically a table of coordinates with some observability, and then you can play games and see how you can optimize this better. Some tests done in this direction are here. So for example, if you want to reduce your slewing time, you don't want to usually go like to the center and then up, down, up, down, up, down, as that's what the scheduler is going to propose based on probability, but you rather want to do something that is more smooth and goes like tack, 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 and doesn't go like very extreme from one side to the other. Okay, now where can you find tilepy? So tilepy is being used for scheduling in HES, scheduling in CTO LST1 and MAGIC as well. You see here a case for LST1 plus MAGIC observations, and also in observation prospects for CTAO. But obviously you can also find it in Astro-COLIBRI and in tilepy API. Focusing on Astro-COLIBRI, yesterday Fabian did a little demo on how you can obtain all the scheduling for your gravitational wave based on how you change your the location of your observatory. So it's very simple to use. You just need to wait for a minute or more, depending on how big your uncertainty region is. But once you wait for that, you will have the scheduling for that line. Okay, so The outlook of tilepy, well, this is our to-do list. We still have some things that are ongoing that I presented, but they need like the final fixes. I didn't mention, but we have also included the possibility of having different field of use. That's something that in the past we were just focusing on circular, because tilepy is basically motivated by the cases we want to cover. Technically, we've improved a bit. So now we have some GitHub workflows for continuous integration. The code is in PyPy, and also there's a read the docs for tilepy. Okay, so if you want to know more, just check one of the different places where tilepy is. And with this, I finish. I'll be happy to take questions.